All right, so I got some old quiz problems for you to think about. They're all in electric fields. And so I want to start out just by generally outlining the way I think about electric fields and the way I hope that you would. This idea of fields is invented, basically, to talk about forces between two things that aren't in contact with each other. So if there's two objects that are separated from each other by a big distance, and yet they're both positively charged, and you can tell that they're pushing away from each other, that's what this idea of electric fields is meant to represent. One of the charges, so here's the two parts to this. One of the charges produces a field everywhere in space. I say one charge, but any set of charges can produce a field everywhere in space. And that could be an electric field, that's a vector field, we're going to work with those. But it could also be an electric potential field, that's a scalar field. So if there's a charge sitting here at some location, then it produces a voltage everywhere. So that's a scalar quantity, it doesn't have a direction, it's just a number and a sign. So we'll work with both of those, but these are invented and talked about in essentially to get to the end, which is other charges feel these fields. So if an other charge if there's an electric field at some other charge Q, then Q times that electric field is the force on Q. It feels the electric field that sits at its location. Or potential energy. If there is an electric potential, a voltage, at charge Q, then there is an electric potential energy. That's just Q times the electric potential. So those are that's the general picture that we use fields for. One set of things produces a field. Another set of things, electric charges, feels that field. Well, the same general picture for magnetic fields, but I'm not going to talk about those today. All right. First quiz had two questions. The first one is, well, the problem is that there are four charges arranged on the points of the corners of a square, A, B, C, and D. All four objects have the same magnitude, positive electric charge. Use a picture or calculation to show that the electric field at the center of the square has zero magnitude. Zero electric field exactly at the center of the square. Label all the electric field vectors by the object that produces them. So if you draw an electric field vector due to object D, label it E by D. So I'm going to give you a few minutes to work on that, talk about it all you want, and then we'll talk about it. If you get done with that, you can go on to part B. All right, some of you may have moved on to B. I want to make sure everybody has A kind of firmly in mind what that should look like before I let you go on B. Use a picture or calculation to show that the electric field at the center of the square has zero magnitude. Label all electric field vectors by the object that produces them. So the way I would draw electric fields at the center usually would be to draw a vector that's at the center, that starts at the center and goes in the direction it's supposed to go. It doesn't have to be that way, and I'll talk about some differences in a second. But let's do A first. What's the direction of the electric field by positive charge A if you're at the center?
Towards D.
Towards D, or some people pointing down that way, same thing. Away from A, toward D, label it E by A. The electric field by A at that location looks like that. How about by B? The electric field by B, another positive charge sitting there at B, towards C. If you put all of those in, so this would be E by B. From C, it would be an electric field that way, E by C. And I'm not doing this very well, but let me try to do it better. Electric field by D points away from that positive. They're all 4 positive charges. The electric field point away. If you are at the center, then you draw a vector that points, for each of them, you draw a vector that points away from that charge. The equation down here tells you that the magnitude of that vector depends on a constant k, which is the same for all of them, depends on the magnitude of the charge, which is the same for all of them, and 1 over the distance from that object squared. If you're at the center of the square, then the distances from each of those is the same, so the magnitude is the same for each of them. Because it's a square, these are all at right angles with each other. And so you can see the electric field by C cancels the electric field by B. The electric field by D cancels the electric field by A. And so they add up to 0 because they've completely canceled each other out. Because of the symmetry of the picture. Now, one of the reasons I wanted especially to do this one, because I've seen, I'm not sure I've seen answers to this one, but I've seen people who, let me get rid of this particular set of pictures, which is just the way I would draw it. You could equally well draw the electric field by D. I don't think we have rules on this. You could draw the electric field by D and end the arrow at that point. I mean, I don't think that that's logically incorrect. You can end the arrow at the center instead of starting it at the center. But then you should do the rest of them this way. This would be the electric field by A. And then the electric field by C, pointing away from C, would be that one, and the electric field by B, pointing away from B, would be that one, and they would still cancel each other. And so I think that drawing it that way is also fine. What I've seen, though, people do, is draw things that look like electric field lines. Like in this picture right here, they'll start something there, and maybe your picture looks like that. Start something at the charge, and draw a vector to the point that it needs to be. And to me, if you draw the vector at the charge, I have this feeling that you've drawn an electric field line. Otherwise, why would you start it at the charge? There's nothing special about the charge. The only special point is the location where we want to know the electric field. So I would say you either have to start your vector there or end your vector there to make it clear. And starting your vector at the charge, things like that make me feel like you've drawn electric field lines rather than electric field vectors. And so I want to make sure that you don't do something like that. I mean, if I want to draw vectors due to A, electric field by A, Then there I could draw the electric field like that. What about some other location? Well, at this point, that's about the same distance. But it has to point away from A. I'm not doing a very good job of this. It has to point away from A. So here's another electric field vector by A. And I can draw one down here. There's an electric field vector by A everywhere in space, so I can put them anywhere. There's a vector down here, points away from A. It's maybe 50% farther, so it's maybe half the length of this one. Who knows exactly, but it's definitely shorter because it's farther away. So electric field by A down there looks like that. If I'm even farther away, like right here at point D, the electric field is only 1/4. I'm twice as far away, so the electric field down here at point D, the electric field there is only about 1/4 what it was in the center. The electric field vector can be drawn, an electric field vector can be drawn for any point in space. It's not the same as electric field lines, which start on positive charges and end on negative charges. And they go until they end somewhere, so they can run off the page sometimes. All right, after all that, I'd like you to think about B. In particular, not just your answer to B, but how to show it, how to prove it, what you're going to draw, and what you're going to say that explains the issue. So in B, what we're going to do is put a small positive charge at the center. Okay, we've already shown from A there's no electric field at the center. So that small positive charge at the center has no force on it. No force on it is what we would call an equilibrium point. Now the question is it an oscillator? So is there a restoring force? If you push the small positive charge slightly away from the center, is there a net force pushing it back toward the center? If there is, then it's going to oscillate. And if there isn't, then it won't oscillate. So the first question is about a positive charge. Decide how you're going to answer that one. Then the next question is about putting a negative charge at the center. Is that an oscillator? So, as I say, your answer is whether it's an oscillator or not is not as important as your discussion on why you answered what you answered. So think about a charge that's been, I'm going to draw these diagonals in because to me there's two directions that make sense here. One is, think about a charge that's pushed toward one of the charges. Say I push it toward B. If I push a positive charge in the center toward B, is there a restoring force? Another direction would be in between these two lines. So suppose I push it along a horizontal direction, not toward A or C, but in between. Is there a restoring force? So I will suggest you think of those 2 points. Think of finding the total electric field at each of those 2 points and deciding if there's a restoring force for a positive charge or a negative. Give you a few minutes to sketch those out. Okay, so let's draw the same four vectors, and by that I mean the electric fields due to the same charges, but at these different locations. So if I move over to here, let me get rid of this dot in the center for a second. If I move over to here, there's still an electric field by B that points away from B. Bigger or smaller than it was? Gets bigger. Not sure how big I drew it before, but I'm going to write this. Electric field by B is bigger. The electric field by C still points away from C. Bigger or smaller than it was? Smaller, farther away, so now this one's smaller. I should probably be more careful than I am here about the magnitudes, but I hope you can see what's going on, even if I'm not very careful about the magnitudes. But that one gets smaller, this one gets bigger. How about A? It's a little farther away, so probably got a little smaller. Whoops, wrong direction. Electric field by A points away from A. And electric field by D is a vector pointing away from D. Now, if I put those three vectors together, as I say, I should be a little more careful, but because it goes as the distance squared, the biggest change is going to be that distance, the amount that I went toward B, because it's rising as 1 over the distance squared. So as I get closer to B, it changes by more than it changed when I got farther from C. So E by B is going to be the biggest, by far the biggest vector around. And if you add those three together, I think that you'll see that the net of those three is a vector toward the origin. Sorry, toward where we started out, the equilibrium point, toward the center. That the net of all of those four is going to be a vector toward the center. So if it's a positive charge, what's the direction of the force when you push it that way? In the direction of the electric field, toward the center. What if it's a negative charge? Away from the center, toward B, in fact. If it's a negative charge and you push it toward B, suddenly there's a big electric force toward B. The electric field, the net electric field points away from B. At this point right here, when I've pushed something toward B, if the electric field points away from B, then a negative charge feels a force toward B. So it looks like maybe a positive charge will be an oscillator because it has a restoring force. It has something, when you push it away, it has something to push it back. And a negative charge won't be. You push it away, and it's just going to keep on going. That's a little like, the classic analogy would be a ball in a cup that's in a spherical cup. It can, if it sits in the bottom of the cup, it can sit there at equilibrium. If I push it away, I roll it up the cup a little bit and let go, it rolls back down and it rolls back and forth and just oscillates. But if I flip the cup over and I put the ball right at the top, it's still at equilibrium like that negative charge is, but when I push it just a little bit away, it rolls right off the cup and goes away from the equilibrium point. So it's the difference between the positive and the negative charge is just like the difference between a bowl that is upright and a bowl that is upside down, and a ball on that bowl. Yeah?
For the positive charge, when back to the center, how could it be going away from the center?
The positive charge, if I push the positive charge away, it gets pushed back toward the center. So if I push the positive charge toward B a little bit and then let go, it'll be pushed back toward the center. It'll go faster and faster. Once it gets to the center, there'll be no force because that's an equilibrium point, but now it's moving. And so it keeps moving, and now there's a force that slows it down because the force, once I get back to the center, is still the force. As I go closer to C, the force ends up pushing the positive charge toward the center again, so it slows down. And basically, the positive charge is going to oscillate back and forth like that over and over and over until it loses that energy that I gave it by pushing it. Well, there is this other direction, so it's worth thinking about. Not other direction, but there are other points in space. And while I suggested first let's think about pushing it directly toward B, what if we pushed it in between these two dotted lines? What happens to the electric fields then if we push them in between the two dotted lines? Well, I've gotten closer to A, so the electric field by A is going to be a little bigger than it was. The electric field by D is going to be a little smaller. Than it was. So I got closer, a little closer to A and a little closer to C and farther from B and D. What is C going to look like? Again, I'm closer. So electric field by C, I didn't label this one. This one's supposed to be by D because the electric field points away from the positive charge, so that's the one pointing away from D. And then B, I got farther from B also. So there's an electric field pointing away from B. Now, again, I really should measure the distances, do a calculation, find out how big these vectors really are. But you can, I think, see kind of what's going to happen. If I add these two together, I end up with an electric field like that by C and A. If I add those two together, I get an electric field by C and A total. I've drawn it with double lines just so it'll be distinct from the other electric field lines I'm drawing. And if I add these two together, I get an electric field by D and B that looks like that. And again, I should be really careful with the magnitudes, but even as I've drawn it, the magnitude, the electric field by C and A is larger than the electric field in the other direction. So it still looks like there's a restoring force toward the center. You know that's going to stop at some point, because if I push a positive charge, let's say I push it all the way. Let's say I don't just push it a little bit. Let's say I push it all the way over to here. If I put a positive charge all the way over to here, then all these other positive charges are to the right. So there will be a force to the left, and it will get pushed. It'll just go away. So this oscillation is not it's not a harmonic oscillator no matter how far you push it. If you push it too far, it'll run away from these positive charges. But as long as you keep it in the center, there will be a restoring force that somewhere out here it'll stop being a restoring force, and you'll have to be really careful to decide where. But there will be a restoring force as you push it away until you get somewhere out here, and then it'll go the other way and stop being a restoring force. That's the same thing as saying, I said that there was a cup. It was like a ball in a cup. It's like a cup that has a height. So if I push the ball too far, it'll run out the outside of the cup and it won't come back in again. Any questions about? I like this one because it makes you draw electric field vectors in all sorts of different places and have to think about the magnitudes and the directions all the time. And that is a good exercise for whatever exam comes up, probably. Yeah?
For negative charge in the second, pointing it towards that direction, would that also be oscillating?
A negative charge along this direction is going to have a force in that direction. But once it gets too far, it'll have a force back. So just literally along that direction, you're right. But along this direction, a negative force will be like a ball that rolls back. A negative charge will have a restoring force somewhere toward a point in the middle. Toward a point over here. It'll be pushed that way, and then if it gets too far, it'll be pushed back. But what if it's not exactly on that line, but it gets a little bit up there? If it gets a little bit up there, then this force due to that positive charge A is going to take over, and it's going to get sucked over to there. So it's not like, it's like the negative charge in that particular direction. Sure, it's like the thing that can oscillate, but in these other directions, it's a downhill motion in the other direction. So it's like a ridge. Sure, it can oscillate on that ridge, but all it has to do is move just a little bit, and it'll fall off one end of the ridge. And so that's what is going on in that kind of problem with the negative charge. It's not a very good oscillator, the negative charge. Yeah.
And wouldn't it be true that there would be, the point that it oscillates around would not be the center?
It definitely would not be the center. That's right. The negative charge is being pushed away from the center. But what she was noticing, I think, is even though it gets pushed away from the center, if you went far enough away from the center, you can tell it's being pulled back again. So there has to be a place along this line where there's no force on the negative charge.
Well, equal force.
Not no force. Where there's equal force, yes. There's... no electric field left or right. All right, any other questions on that one? All right, electric potential. Also, since it has units of voltage, I'll say also known as voltage. And I've written it here. The first part of our electric field picture of electric interaction says electric charges produce fields. They produce electric vector fields. We talked about those in the first problem. They also produce electric potential fields. And that's a scalar quantity. That's not going to be a vector. That's just going to be a number at every point. And what's drawn here in what's drawn here and what's explained here, the figure to the right has a charged particle A at the center with 4 lines of constant electric potential. So this A particle, as in number 1 here, electric charges produce fields. That A particle has produced an electric potential field. It's negative 20 volts along here, everywhere on that line. Negative 10 volts everywhere on this line. Negative 5 volts everywhere on that line. Negative 3 volts everywhere on that line. You can tell that the voltage is going up. It's becoming less negative as you get farther away from that charge. It's symmetric because it's a point charge, so there's circles. You put an electrically neutral polar molecule here. So we've talked about this. This is the ball and stick picture of a molecule made up of 2 oppositely charged pieces. The ion over here, the B ion has a charge of -1. The C ion has a charge of +1. First question, the first problem, estimate the potential energy of the polar molecule in this location and in this orientation. So, calculate the potential energy of the molecule. I'll just remind you that potential energies are additive. Energies are additive. So if you know the potential energy of B and the potential energy of C, then you can add them together to get the total potential energy. And then once you've got a number for that potential energy, how does that number change, or does it change, if this molecule rotates? So part B is about whether it rotates. So just think about it rotating without changing its center of mass. C is, I'll let you think about. D is about translational motion. So whether or not it rotates, does it move, does the center of mass move in any particular direction? So that's what all these questions are about. And right now, just because it's practice with electric potential, I'd like you to use energy arguments for all of your answers. So let me remind you, my standard way of reminding people of energy, the direction that something wants to move, if you release it from rest, is toward lower potential energy. If I release that piece of chalk, it drops. Why does it drop? One way of discussing that is because the potential energy goes down in that direction. So this molecule will move in such a way as to lower its potential energy. Whether it rotates, or whether the center of mass moves, or whether both of them happen. It'll do that in order to lower its potential energy. So that's the question you want to think about when you're thinking about its motion. Give you a few minutes to talk about that and construct an answer for these problems. All right, let's talk about this a little bit. I know I'm probably cutting you short, but I want to give you a chance to look at and think about one more problem after this. Maybe there's time. So the potential energy of particle B, of this part of the molecule, this ion B, is the charge of B times the electric potential at B. What's the electric potential at point B? Approximately -6. Charge of B is -1. Electric potential at B, -6 volts, approximately. Charge of C is 1, +1. What's the electric potential at point C? Yeah, maybe -8. I mean, it's changing as you get closer and closer. You can see that it changes faster and faster. So the difference between 3 and 5, this is 2 volt difference, and then the smaller difference in distance is a 10 volt difference. Sorry, a 5 volt difference, and then there's a 10 volt difference, and even the smaller distance. So the electric potential, the voltage, is changing really rapidly. It's dive bombing as you get close to going more and more negative really fast as you get close to A. So this is changing pretty fast here, but it's a little less than 10. So I don't know, let's call it 8. It doesn't.
Negative.
Thank you. -8. So what do you get here? You get 6. I don't know what the units of that are. I'm going to pretend it's coulombs, and I'll write 6 joules. And I don't know that it's joules because I don't know the units of that because it doesn't say here. But I'm going to pretend it's coulombs, and then that would be joules. Minus 8 joules minus 2 joules for the total potential energy. So motion. Just think about rotation. If you just rotate that slightly clockwise, what happens to the what is this potential? What happens to the energy of this thing as you go slightly clockwise? Well, this will move to the right. This will move to the left a little bit. A little bit to the right here. Is that a bigger or smaller change in potential energy than this one moving a little bit to the left? It's bigger because as you get closer, this is changing faster and faster and faster. So this one up here that's closer, when it moves to the right, its energy will go up or down. That's 1. Negative 8. If it goes to negative 9, that's gone down. What about this one? This is negative 1. If it moves to the left, it's gone from 6, say, to 5. So that's also gone down. The potential energy of both of them go down in a clockwise motion. If you want to discuss this simply in terms of energy, that's what you would say. Both of them lower their potential energy by going clockwise. And so I don't have to worry about how much lowers one more than the other. They both lower their potential energy by going clockwise. So clockwise motion is the thing that will happen because that's the thing that lowers the potential energy. Counterclockwise will raise the potential energy. Is the electric charge A negative or positive? Just essentially the definition of, for a point charge, the electric potential depends on the charge. So if the charge is negative, then the electric potential due to that charge is going to be negative. And as R gets smaller, as you get closer and closer, that negative number gets more and more negative. So this is a negative charge A. Does this molecule move toward A or away from A? Yeah, that's an issue of how much the energy went down. As this thing rotates, the energy of, or if it moves, if this center of mass moves toward the right, then the energy of this positively charged particle is going to drop. The energy of this negatively charged particle, B here, is going to go up as I get closer, but B is farther away. So C is closer. It's going to drop more than B goes up. And the end result is that this thing is going to want to rotate clockwise, and A is going to suck C over toward it. So it's going to want to rotate clockwise and move toward the negative charge. Yeah? You could. I just would like you right now to think of these things in terms of energy, but yeah, if you drew a force diagram, then because C is closer, you would have a bigger force for C than the force away from, than the force at B. And so the net force would be to the right, but it would also be a net clockwise torque. So this thing, in part B, it says specifically use energy arguments. So calculate potential energies and decide how the potential energy will go down. Yeah.
It says sketch an energy interaction diagram. Would you take just using the potential energy equation, like just showing that the charges decrease in potential energy?
I definitely would. Yeah, I'm not sure I would say sketch an energy interaction diagram.
Thank you.
Just, I don't know, just because you haven't done it in so long and we're not going to be able to hold you accountable for initial state, final state. There's a lot of things that I wouldn't want to put on your back right now. So an intelligent discussion of the energies of this problem, I would say, is good enough. All right, I just want to I want to say a little bit about this. I'll leave you all to work on it on your own. I got this. This is one of the example quizzes posted on SmartSite. This is the second problem in it, and I wanted to throw it up here so I could make a point and give you something to think about. what it shows is a cart moving on a track. The cart is negatively charged. Okay, so the cart is going to have a force opposite to the direction of the electric field. Down here is a picture of the electric field at various locations on this thing. This says it says the care, but what it means is the cart has enough speed to make it all the way to point B. So the cart is probably moving at the beginning. So what's going on here? The electric field is to the right at the beginning, so the cart has a force in what direction? To the left. It's slowing down. Here the electric field is smaller, but it still points to the right. So what's the direction of the cart? Of the force on the cart? Still to the left. Not as big, but it's still slowing down. Here, there's no electric field, so there's no force on the cart. However much it's slowed down, we know it gets to the point B at the end, so we know it's still moving there. Here, the electric field is to the left and getting bigger and bigger. So what does that tell you about the force? The force has to be to the right and getting bigger and bigger. So this thing is picking up speed. So it was slowing down, then it's going faster and faster and faster. Where is it going the fastest? So 8 meters, 9 meters, 6 meters. What's going on at 8? Is it being speeded up or slowed down? Which is the direction of the force at point 8? To the right. It's moving to the right. It's got a force to the right. Does that mean it's speeding up or slowing down? If you push something in the direction it's already going, it'll go faster. It's speeding up all the way through here, and it's going its fastest at 9 meters. Because at 10 meters, we know it's something slowing it down already. So it's going its fastest at 9 meters. That's just in terms of forces you can talk about that. You can also talk about it in terms of energy. And I don't think I have, not sure I have time to do this, but let me just say, or remind you, that the electric field delta R, delta X, what do we call this? Delta X, I don't know, horizontal distance. The magnitude of the electric field tells you it's equal to the gradient. I'll just put magnitudes everywhere. Let's make everything positive right now and not worry about the sign. The magnitude of the electric field is equal to the gradient of the potential energy. Whoops. The gradient of the electric potential and I want to remind you from 7a that the gradient, the slope of the potential energy curve, told you about how big the force was. But the force is related to E, and the potential energy is related to the electric potential, both by this same Q. So the electric field, the magnitude of the electric field vector tells you about the gradient of the electric potential. And so I just wanted to say, what do you see right here? 50, 100, 200. You see an electric field that's changing really fast. In a small distance, it goes up by 100. What did it do over here? Well, it went down by 100 in the small distance. But anyway. No, sorry. In this small distance, it's changing by 100. In this small distance, it's changing by 50. And in this small distance, it's changing by 50. This right here, as the electric field points to the right, is an electric potential. Shoot, I've run out of time. I'll just say you can think of this in electric potential terms and electric potential energy terms also. I don't want to take too long here.